Hello, everyone. Welcome to the ILTA Physics online problem-solving lecture. Today, we are going to study the concepts of mass and weight. In everyday life, we often use these terms interchangeably, but in physics, they are distinct concepts. They even use different units. Mass is an intrinsic physical quantity that an object possesses, while weight is the force exerted on an object due to gravity. The image below shows astronauts working in a zero-gravity environment inside a spacecraft. Even an object with a constant mass can experience a very different amount of actual force depending on where it is located. To put it metaphorically, mass is a unique quantity representing the essence of an object, whereas weight is the magnitude of the force determined by the object's location. To add one more thing, apparent weight can be described as the physical quantity we actually perceive through our senses based on the object's state of motion. Today, we will solve problems related to apparent weight as it relates to an object's motion, using mass and weight as our foundation. We will also think about a special state where the apparent weight becomes zero, which is known as weightlessness. Now, let's briefly summarize these physical quantities. Mass is the inherent amount of matter in an object. It is an essential value that does not change regardless of where the object is or what forces are acting on it. On the other hand, weight is the magnitude of the gravitational force pulling that object toward a planet like Earth or the Moon. Therefore, if gravity changes, meaning, depending on which planet the object is on, the pulling force changes. Since weight is a force, it can be calculated as the product of mass and acceleration according to Newton's second law. Generally, weight is denoted by W, and the acceleration due to gravity on Earth is 9.8 meters per second squared. In addition to this, the concept we will focus on today is apparent weight. Apparent weight is not the actual weight of the object, but the magnitude of the force felt depending on the object's state of motion. For example, we usually feel our weight through the normal force, which is the force the floor we are standing on exerts to push back up against us. The most common example where we can feel apparent weight is in an elevator. When the elevator you are in accelerates upward, your body feels heavier. That is exactly what a change in apparent weight feels like. The calculation of apparent weight can be divided into three cases based on the object's state of motion. For detailed physical explanations, please refer to my theory lecture. Here, I will just summarize the final formulas. First, when the object is in a state of equilibrium. In terms of motion, equilibrium means the object is either at rest or moving at a constant velocity. Since the acceleration is zero in this case, the apparent weight is equal to the actual weight. If you are in an elevator accelerating upward, a force proportional to the acceleration is added to your original weight, making your body feel heavier. Mathematically, the apparent weight is calculated as the mass times the sum of the gravitational acceleration and the object's acceleration. The most important point here is that the object's acceleration is applied in the upward direction, that is, in the opposite direction of the acceleration due to gravity. Conversely, if the elevator accelerates downward, an amount of force proportional to the acceleration is subtracted, making your body feel lighter. This is where we can explain the state of weightlessness. If the downward acceleration of the elevator becomes exactly equal to the acceleration due to gravity, you experience weightlessness where your apparent weight becomes zero. It would feel as if your body is floating. If we ignore air resistance, all objects in free fall experience weightlessness. Many problems frequently ask about apparent weight in combination with the object's motion. Problem number 19 asks for the apparent weight felt by a 60-kilogram passenger at different stages of an elevator's motion, as it accelerates from rest to 10 meters per second in 4 seconds. When dealing with apparent weight problems in a moving elevator, you should first think of a free body diagram like the one shown on the right. We will set our coordinate system as a Cartesian system where the positive y-axis, or the upward direction, is the positive direction of motion. Since the problem states the elevator accelerates upward from the first floor, the direction of the elevator's velocity is upward, and the direction of acceleration is also upward. In this problem, the apparent weight felt by the passenger is the normal force between the elevator floor and their feet. According to Newton's second law, the law of acceleration, the vector sum of all forces acting on an object is equal to the product of the object's mass and its acceleration. What is important here is to note that because the acceleration is upward, it will be a positive value according to our coordinate system. There are two forces acting on the person: the weight pulled downward by gravity and the normal force acting in the upward direction. Writing this as an equation considering the directions, it becomes the normal force minus the weight. Since the normal force is the apparent weight in this problem, we can calculate it by multiplying the mass by the sum of the gravitational acceleration and the acceleration of motion. In other words, since the elevator is accelerating upward, we can calculate the apparent weight simply by finding the acceleration for that stage of motion. First, when it is still at rest. Since it is in equilibrium, the acceleration is zero, so the apparent weight is equal to the actual weight. Multiplying 60 kilograms by the gravitational acceleration of 9.8 gives approximately 588 newtons. Next, when the elevator is accelerating upward. The acceleration of the elevator is found by dividing the change in velocity by time interval. Since the velocity changed by 10/4 seconds, it is accelerating at 2.5 meters per second squared. Therefore, our body receives an additional force equal to the upward acceleration on top of the original downward gravitational pull. We multiply 60 kilograms by the sum of the gravitational acceleration 9.8 and the elevator acceleration 2.5. This calculates to 738 newtons, making the person feel heavier than usual. Now, when the acceleration ends and the elevator moves at a constant velocity. Constant velocity is also a state of equilibrium, so the acceleration becomes zero again. At this time, the apparent weight returns to the actual weight of 588 newtons. Please make sure you clearly understand how apparent weight works when an elevator accelerates upward. Problem number 21 involves an elevator that was going down at 10 meters per second and gradually slows down to stop at the first floor. Let's find the apparent weight felt by an 80-kilogram passenger. There is something to be careful about here. Although the elevator is moving downward, it is slowing down to stop, so the direction of acceleration is upward. It is like the elevator is being pulled upward to reduce its. The drawing on the right shows the motion of this problem as a free body diagram. Please note that while the direction of travel is downward, the direction of acceleration is upward. First, before the elevator starts to slow down, when it moves downward at a constant speed of 10 meters per second, it is in equilibrium. The acceleration is zero, so the apparent weight is 80 kilograms times 9.8, which is 784 newtons. Now, let's look at the section where the brakes are applied and it slows down. According to the acceleration formula, the initial velocity is -10, the final velocity is 0, and the time interval is 3 seconds. The initial velocity is -10 because, according to the coordinate system we set, the direction of motion is downward, which is the negative direction. Calculating the acceleration gives 3.33 meters per second squared. Since this is a positive value, we can confirm the direction of acceleration is upward. Therefore, the apparent weight is calculated by adding 3.33 to the gravitational acceleration of 9.8 and multiplying by 80 kilograms, which equals approximately 1,050 newtons. Even though the elevator is going down, the body feels much heavier than usual. Ultimately, I hope you clearly understand that what determines the apparent weight is the direction of acceleration, not the direction of the object's motion. Problem number 23 provides a velocity time graph of an elevator and asks for the apparent weight felt by a 75-kilogram passenger at 1 second, 5 seconds, and 9 seconds. First, let's look at this velocity graph to understand the elevator's motion. The fact that all velocity values are positive means the elevator is constantly moving upward. Please look at the diagram below and understand that the elevator is moving up as time passes. For the first 2 seconds, the velocity is increasing, so the acceleration is in the same upward direction as the velocity. From the 2-second to 6-second interval, it continues to move up at a constant velocity of 8 meters per second. Since there is no change in velocity, the acceleration is 0. In the 6-second to 10-second interval, it is still moving upward, but the velocity is gradually decreasing. Note that the acceleration in this case points downward, opposite to the direction of velocity. Now let's calculate the acceleration for each interval and find the apparent weight. At 1 second, since the velocity is increasing at a constant rate, we calculate the acceleration by the difference between initial and final velocity, which gives us 4 meters per second squared. So we add 4 to the gravitational acceleration 9.8 and multiply by 75 kilograms, resulting in a weight that feels heavier than usual. At 5 seconds, the velocity is constant at 8 meters per second. It is moving, but it is in equilibrium with zero acceleration. Therefore, the apparent weight is 75 kilograms times 9.8, which is 735 newtons. At 9 seconds, it is moving upward, but the speed is decreasing. This means the acceleration is acting in the downward direction. Calculating the acceleration gives -2. This time, we subtract 2 from the gravitational acceleration 9.8 and multiply by 75 kilograms. The result is 585 newtons, making the person feel lighter than their actual weight. In today's lecture, we learned about the difference between mass and weight, and how apparent weight changes according to acceleration. You just need to remember that weight is added or subtracted depending on the direction of the acceleration. That's it for today's lecture. You all did a great job. See you next time.